All right, so let's think this through. What's going on here? So going back to the formula for a second, remember all the clauses end up being in these groups. So there's one clause for each node that says that node has to have one of the k colors. So that's going to total up to n clauses in the formula. Then for each pair of colors, we have to exclude that they're both true for every node. So this is for every node, for every pair of colors in the node, there's a clause. So for every node, for every pair of colors, there's a clause. All right, and that covers making sure that there's a color assignment that makes sense. Then, for each color, for each edge in the graph, we have a clause that excludes that color is shared on both ends of that graph. So that's for each color, for each edge, we have a clause. So that ends up being the total. There's no other clauses that we need to consider here. That captures the notion of k-colorability. So we can just plunk these numbers in. 8 plus 8 times 3 times 2 divided by 2 is 3. 3 times 20 is 60. 92 is what I get. But the important thing that I wanted you to get at is this formula here, which most importantly is polynomial in the size of the graph. So we have a graph of a given size that from that we generate a formula, and that formula has a given size, and that size is polynomial. So that's good, because then when we run, imagine that we have some kind of satisfiability algorithm that runs in polynomial time. It's running on a polynomial-sized input. So it's not like we're running a polynomial time algorithm on an exponential-sized input, which will take exponential time to run. This way, it really does run in polynomial time.